Today's lesson is how to explain the traditional algorithm of multiplication. Now, before we start in on that, we need to understand what the words traditional and algorithm mean. Let's start with traditional. The word traditional means the usual way of doing something, or standard. Make sure that you are writing down these definitions in your notes. And the word algorithm means a set of rules or steps you follow to get the correct answer. And what's really key about algorithm is that the steps have to be followed in a certain way, in a certain order, every single time in order for it to work. Now, we've learned some traditional and some non-traditional ways of doing things in the past. Take addition, for example. You do not need to write this down in your notes because this is something you've already learned. We're just connecting it to what you already know. The traditional addition algorithm looks something like this. Working from the ones place to the tens place to the hundreds place in that set order, and with the rule of regrouping when we have too much, like a 15, to go in just the ones place. But sometimes, depending on the problem, it's actually more friendly and more efficient to use some non-traditional addition strategies, such as a tree diagram, compensation, and a number line, to name a few. So just like we have different strategies that we can think of and models that we can show addition and subtraction, we also have different strategies that we can think of and models that we can show for multiplication. And we're going to take this time to explain why the traditional algorithm, the standard way of doing multiplication problems, actually works. Now, when I was in school learning multiplication, my teacher would put problems on the board and she would explain the steps and she would say, "Do this." And I was like, okay. And my classmates were like, "But why does it work?" Or just plain, "Huh?" At which point our teachers would promptly say, "Because it just does. So just do this and you will get the right answer." So we nodded along and we memorized the set of steps that would miraculously, magically get us the right answer. And since we didn't really know why we were doing the steps and carrying the numbers and placing that extra zero, we were really likely to forget to do it at all. Because if you don't know why you're doing something, you're probably not going to remember to do it. So that was a problem. Now, I am in no way saying that the traditional is bad and that the weird and new is good and happy and shiny. What I am saying is that we need to be able to explain why it works, not just because my teacher told me so, and if I follow these rules, I get the right answer, so it does. We need to know why, so we're likely to not make some common mistakes. So let's dive right in and show why all of these traditional ways actually work. Now, you should have learned how to do a problem like this in 3rd or 4th grade, and hopefully your teachers explained why. If not, though, here's a very quick refresher course before we go on to working with like 6 digits at a time. So here we go. Typically, we would say 7 times 8 is 56. Write down the 6, carry the 5. So we've split up the 56. But really, we're not carrying a 5. We're carrying it over into the tens place. We're carrying the 50 of 56. And that's why it goes over and spills over into that tens place. So we have an extra 5 groups of 10 or an extra 50 that we'll have to take care of in this next step. And that does bring us to our next step. Then we go 7 times 5. So first what we did was we distributed the 7 to the 8, and now we're distributing the 7 to the 5. But check this out. Is it really a 5? No, it's in the tens place. So this is really a 50. So what we're really saying is 7 times 50, which, if I use my cheating with zeros trick, 7 times 5 is 35, and place 1 0 from the factors in the product. So really that's 350, but wait, we can't forget about this extra 5 in the tens place, which is an extra 50. So what we need to do is we need to take this 350 plus our extra 50 from before, and that brings us to 400. Now, I can't really cram 400 into just the tens place. Doesn't work that way. So what do we need to do? Well, we see that there is a 4, which is our digit of value here, but it has to be in the hundreds place. And right here, we're just working with the tens place. And here's our tens place. Anything? Nope. So our tens place is going to be a 0, and our ones place was 2. And that 400 is going to go on a journey. It's going to travel over here to the hundreds place. This shows that there wasn't enough room for 400 in the tens place, but we can put 400s in the hundreds place. And now it's time to distribute our 7 to the 2, which is not really a 2, but a 200 because it's in that hundreds place. So really what we're doing is 7 times 200, which would be 7 times 2 is 14. Place 2 zeros. 1,400. But wait! We're not done yet. We have that extra 400 that spilled over from before that we need to take care of as well. So we don't just have 1,400, but we also need to take care of that extra 400, which would equal 1,800. Okay, I can't really cram 1,800 into that space because it doesn't work like that. So we need to look at our digits of value, the 1 and the 8. First of all, what we can see is that we don't have any more distributing to do. We don't have any thousands or 10,000s to multiply by 7. So we're done with our multiplication distributing. So what we can do is we can just make sure that this 18 here for our 1,800 gets in the right place. So if we take it and we move it on over, all of this all at the same time, the 8 can go in the hundreds place, just like it is right here. And the 1 can go in the thousands place, just like where it is right here. So that's why we're adding these extra groups that spilled over. A common misconception is that you multiply it, like the shortcut, 7 times 5 is 35, times 5 is some gargantuan number. No. It just means that you have an extra 5, really a 50, to add in when you're all done. So that's how the distributive property works as we go from one place to the next, and why we carry over to the next place. It all has to do with place value, and that's why we've got to keep our columns straight. Otherwise, we get all confused. Now let's take a look at how this works with a more complicated 5th grade level problem. Be sure to write this down in your notes, including all of the stuff that goes on over at the side, just for this one problem, so that you can explain why it works. Because I'm not going to let you use this algorithm unless you know why it works. All right, so let's get started here. We're going to distribute the 5 to the 4, the 5 to the 1 that's in the tens place, which is really a 10. The 5 to the hundreds place, there's an 8 there, so that's really an 800. and the 5 to the thousands place. There's a 3 there, and it's really worth 3,000. Now with other strategies and models that we've used, like the area model and like the ratio tables and partial products, as long as you distribute and get to all of them, it doesn't really matter what order. But with the traditional algorithm, remember, there is a specific set of rules and steps that has to be followed in an exact way every time in order to get the right answer. So we're going to start with our least valuable place, the ones place, and gradually make our way over to the most valuable place. All right, so let's do this. First of all, 5 times 4 is 20. Well, there's not room in the ones place to write a 20. So we can regroup 20 and think of it as 0 ones and 2 tens. So we have an extra 2 tens that have spilled over. And we got that by going 5 times 4 is 20. Our next step is 5 times not 1, but 10, which equals 50, plus our 20 that spilled over from before, which would equal 70. And that's actually really nice because that's a 7 in the tens place, and our tens space over here is actually available for us to use. So we can just write the 7 right there. All right, our next step is distributing the 5 times the, not 8, but 800, which would be 4,000. You can think of 4,000 also as 40 hundreds. Regardless, we've got a 4 in the thousands place, but our next space right here in our working area is the hundreds place. So what's in the hundreds place here? Nothing. That's where our 0 is going to come from. And our 4,000 is going to spill over into our thousands place. And we have one more step to work with our 5 here as we distribute the 5 times the 3 that's not really a 3, but a 3,000, which would be 15,000. But wait, we can't forget about the spilled over 4,000 from our last step that we need to add on to this. All part of the same step here, and we get 19,000, which means that we can put the 1 in the 10,000s place and the 9 in the thousands place and be just perfect. Now I've drawn some brackets around the steps over here that were actually 2-step problems because of our spillovers, so we can see what those steps really were. We're now done distributing the 5 to the 4, the 10, the 8, and the 3,000. And you might be starting to look at this and go, wow, 20, 70, 4,000, 19,000, that's kind of looking like partial product there, and in fact, it really is. Now, if you really want to blow your mind, which I know you do, try this. Check this with a calculator. Check 3,814 times 5 and just see what you get. Seriously, do it. Do it now. Press pause. Okay, your mind should be sufficiently blown. Check that out. We've got a partial product of 3,814 times 5, which means now we need to do 3,814 times, not a 9, it's in the tens place, 90. So label this chunk of all of our warm colors here as the 3,814 times 5. And now you just continue down, but I've run out of room to continue below. So you just continue below, but I'm going to have to erase. And we're going to distribute the 9 to the 4, except it's not really a 9, it's a 90 to the 4, the 90 to the 10, the 90 to the 800, and the 90 to the 3,000, which means that essentially what we are doing, and make sure that you write this down, is we're doing our second part, the 3,814 times 90. And we'll show all the steps over here for that as we distribute from one place to another. Now at this point you might have been taught in the past to place an X in that first ones place, or to place a 0, or to place a special kind of placeholder 0 or something like that. I always asked my teacher, why? And they said, because it just works, so do it. But here's why it works. If I am now distributing my 90 to the 4, that means that I'm doing 90 times 4, which would be 360. That means that there is nothing of value in the ones place. And you know what? There never will be. And you can test me on that. You can try it out and see. There never will be anything of value in that ones place. There will be something of value in the tens place, though. In this case, it's a 6, so we can write a 6 in the tens place. And now we started distributing here, so our next area to spill over to is right here. And the 3, this really a 300, has to spill over. But wait, there's already something that's been spilled over here. Well, to make things a little bit less muddled and to be able to keep track of things a little bit better, what I like to do when I go on to distributing with my next place over is I like to cross out what I've already worked with, just with a simple diagonal line. That way I know that I can ignore it from now on, but I don't erase it and I don't completely scratch it out, because if I make a mistake, I want to be able to go back and see what I did so I can figure out where I went wrong and fix it. So just a simple diagonal line. That way I can now spill over my 3 into the next place, and there's room for that spillage. There we go. Now I need to distribute my 90 to my 1 that's really a 10 over here, which is really a 300 to make 1,200. Well, where's that going to go? It can't all fit right here. So let's figure out if this is our hundreds place. What's in our hundreds place over here? The 2. And what needs to spill over because we don't have room? The 1,000. So it can spill over for our next step of distributing. Now I'm going to keep that up high so that this second step of distributing with all the 90s, they're all in a line. Again, in case I made a mistake and I need to go back. So my next step now is 90 times 800. Which, if we cheat with zeros, 9 times 8 is 72, and I've got 1, 2, 3 zeros in my factors, so 1, 2, 3 zeros get placed in the product. But wait, we can't forget about our spillover. We had 1, which is really 1,000 that we need to add to this, making it really a total of 73,000. And that was all part of the same distribution step there. So where do these digits go? Well, that 3 is in the thousands place. That's right here, and I've got space for it. Fantastic. And now this 7, well, there's not room for it in the thousands place that I'm working with right here, so it's gonna have to spill on over. And we have one more distribution step here, the 90 times 3,000, which is, because I can cheat here, 9 times 3 is 27, and 1, 2, 3, 4 zeros, 1, 2, 3, 4 zeros. But wait, we've got some spillage to take care of, and that 7 is really a 70,000. That's where it came from, which would make it 340,000. Digits of value, the 3 and the 4. The 4 is in the 10,000s place, which is awesome because I have a 10,000s place open right here. And since I'm done distributing, I don't have really any need to spill over, so I can spill over right here into the hundred thousands place for the 3. All right, get that calculator out again and check it. 3,814 times 90. It should be 343,260 for a partial product. Seriously, do it. Do it now. Check it out. Blow your mind. So now, just like we always do, we've got some partial products. And we need to put them together. So we need to add them up. I have obviously run out of room for a proper placement of the addition sign, but I know you can do that in your notes. So when we add them up, we should get 362,330. Final answer. So you can see how this really is a more, I would say, efficient way. Instead of listing out all the partial products, which you've got a very long list in your notes, and that's why it is the standard or traditional way of solving it. It only takes up a few lines of your paper, whereas partial products for this might take a lot more room. But you can see there's also a lot of room for error. What if you forget to distribute to a place? What if you forget to spill over? What if you forget to add in that spillage? What if you make a simple mistake when you're adding up those partial products? There's a lot of room for error here, which makes it even more important that we understand why it works. Because if we get why it works, then we're less likely to forget a step because we know how important all of those steps truly are. One last very important step so that you don't end up going through all of this work and getting the very, very, very wrong answer. Your estimate, so that you can ask yourself, does this make sense? Now with multiplication, you can do an estimate beforehand, you can do an estimate after, but you should always do an estimate so that you can ask yourself that. So let's look at our original numbers here. There might be lots of different ways to estimate. A very, very quick one would be just rounding to the greatest place, 4,000 times 100. 4 times 1 is 1, and place 5 zeros. 1, 2, 3, 4, 5. Around 400,000. Is that pretty close to what we got? Yeah, close enough. So, does this make sense? Yes. We know that our estimate was an overestimate because we tweaked both of the numbers up, so we know that our actual answer should be less. And in fact, it is. It does make sense. And hopefully the traditional algorithm makes more sense to you as well. Your only task for tonight, and this is very different, is explain to a sibling, neighbor, friend, or parent why the traditional algorithm works. That's all you've got to do. And then have them sign your notes. So that will be proof that you explained it to them. So walk them through it, especially if you are explaining this to someone that's like my age or older. It really might make them go, oh my gosh, my teacher never taught it that way. And you can see why. It is a lot of work. It is kind of complicated to understand why. It's a lot easier to just say the shortcuts, but we won't be doing that in our class because we'll be likely to make a mistake if we don't know why it works. If you choose a sibling, make sure it's a sibling who can actually understand what you're talking about. So I would say 4th grade or older. Enjoy this, get ready to blow some people's minds, and I'll see you back at school.